In this problem, I'm being asked to use the first derivative test to determine the local extreme values of the function and identify any absolute extrema. And then I'm going to support my answers with a graph. So, you know, I like to get a good sense of what the function is telling me. So I generally like to start out with the domain. And I can see that this function right here is a polynomial. So I know that the domain is negative infinity to positive infinity, all real numbers. The other thing that I'm kind of like to keep in my head here is what is the end behavior of this function? So if I can determine the end behavior, that's also going to help me. And I see that my highest power is odd, and that I have a negative leading coefficient. So I know, for example, that the graph of x cubed, which has an odd power, and it looks like this. But since this has a negative leading coefficient, I know that this graph is going to have end behavior that looks like that. So it's going to be what I call up, down, end behavior. And that'll help me as I go along through this problem. Not mandatory, but helpful. So the next thing I'm going to do is I'm going to find the derivative of my function. So y prime is going to equal to negative 6x squared plus 12x, the negative 3, the derivative is 0. And again, with this derivative function, I also see that my domain of the derivative is also all real numbers. So again, just something I kind of want to keep in my head. Well, since the domain is all real numbers, it means that the derivative exists at all real numbers throughout the entire number line. So the only place that I am going to have a critical point is where my derivative is equal to 0, and that'll also be a stationary point. So 0 is going to equal to negative 6x squared plus 12x. I'm going to just shift it around a little bit. I'm going to say that I'm going to factor out a negative 6x from this. So negative 6x times x minus 2 equals 0. So I can see that where x is equal to either 0 or negative 2, I'm sorry, positive 2, I'm going to have a 0 in this derivative. So let's find out what the value of those points are going to be. So if I take 0 here and I evaluate my equation for 0, I see that I'm going to have one point, one critical point, I'll write it here, one critical point. It's going to be the point x equals 0, y equals negative 3. And if I evaluate my function for 2, I'm going to have negative 2. I'm sorry, for 2 right here, for 2. I'm going to have negative 2 times 2 cubed plus 6 times 2 squared minus 3. Now this one isn't really so hard to figure out, but I just want to show you something that you can do on your calculator that's really going to make your life a lot easier. I'm going to take this function right here, and I'm going to put it into my y1 in my calculator. So I have negative 2x cubed plus 6x squared minus 3. And now I'm going to go to my main screen, and I'm going to go alpha F4, and it gives me a list of all my y equals. And I want the first one, that's where I put my function. So it says y equals, and I'm going to evaluate that function for x equals 2. And the answer is 5. So my other critical point is going to be the point comma 2, 5. Now let's leave that there because that's going to come in handy in just a minute. Now my task is to use the first derivative test to determine where I have extrema, local and absolute. And to do that, I need to divide my number line into intervals. And the intervals are divided by where I have my critical points. So I have a critical point, a 0, right here at x equals 0. And I have another critical point at x equals 2. So I am dividing my number line into intervals, and I have 3 intervals, 1, 2, and 3. And what I need to find now is the sign of the derivative in each of those intervals. So let's take a look at my, my derivative function again. My derivative function is this one right here. So I think I'm just going to write it down here below. Negative 6x squared plus 12x. So negative 6x squared plus 12x. That's my y. That's my y prime. Let's kind of make it look right. Y prime equals negative 6x squared plus 12x. So I need to evaluate the derivative to see whether my slope of my function is positive or negative in each of these 3 intervals. So I'm going to pick a number. I'm going to pick the number negative 1. So negative 6 times negative 1 squared plus 12 times negative 1. Well, that is going to equal, this is 1, that's going to be negative 6 minus 12. I don't really care what the actual number is. That is a negative number. So my slope in that interval is definitely going to be negative. There is no way it can be positive in that interval. It has to be negative because the only places that I can change sign of my derivative are my critical points. And I have no critical points over here. My first critical point is the one right there at 0. So I tested that interval. How about the next interval? Let's delete this. And I have the interval between 0 and 2. So let's use the point 1. So I'm going to go, what is y prime of 1? Well, that's negative 6 times 1 squared plus 12 times 1. That's going to be negative 6 plus 12. Well, that's going to be a positive number. So let's test 1 in the third interval. How about if I test, that's 0, 1. How about if I test 3? So I'm going to test y prime of 3, and that would be negative 6 times 3 squared plus 12 times 3. That would be, so that's 9, negative 54 plus 36. That's a negative number. So in this interval, my slope is going to be negative. So let's just, again, in an estimated sort of way, place our critical points right here on the graph. So I have a point at 0, negative 3. Let's just call it right there. 0, comma, negative 3. I don't have to be precise here. And the point 2, 5. So here's 2, and up here is 5. Here's the point 2, 5. And I'm told that my slope is going to be negative, and then it's going to turn around right at that critical point and go positive, and it's going to turn around at that critical point and go negative. So it's going to look like that. Somehow it's going to look like that. And how does that match up with what I thought my end behavior was going to be? Well, it matches up pretty good. I start up, and I end down, and on my function right here, whoops, I start up and I end down. So I am pretty comfortable with how this is looking right now. So what I'm going to do to check this is I'm going to enter my function into my calculator as a y equal. Then I'm going to go zoom 6, and there's my function. And in addition to this, I'm going to test my numbers, right? I can see that I'm in the right direction, but I have a local minimum right here, and I have a local maximum right there. So let's test it, make sure I have the numbers correct. I'm going to go second, calc, and I want to check to see where I have a minimum. Well, I'm going to make my left bound negative 1 and my right bound positive 1. So I'm looking in that interval right there, and sure enough, I have a minimum x equals, well, it goes 2.2768 e to the negative 6. This is something that you'll see with your calculator. That's essentially equal to 0, and it happens because the pixels on the calculator aren't entirely exact. But 2 point anything to the negative 6 means I'm pulling that decimal point to the left 6 spaces. That's 0, and sure enough, my y is equal to negative 3. How about my other one? Second calc, that's going to be a maximum, and my left bound, let's make it 1. And let's make my right bound, I don't know, 4. And I find that there, my maximum is a 0.25. Again, just as I had it right there. So I'm pretty happy with this result. The last thing I want to point out is that because my end behavior was up going to infinity, down going to negative infinity, my extrema are going to be only local extrema. They're not going to be, excuse me, they're not going to be absolute extrema. I have many numbers that are going to be less than the minimum and many numbers that are going to be more than the maximum.